Hey everyone. I think ZK is a big buzzword, as many of you might know. So a natural question is, what is real in ZK, what isn't? And one other thing that's kind of important is people, when they hear the phrase zero knowledge or zero knowledge proof, they usually think about things like private transactions or roll-ups, compression. I think the goal of this talk is to talk about things that are beyond that are actual applications that people can actually understand. So, both ZK and some of its other kind of neighbors in cryptography land promise sort of a lot of things. The one I think that's sort of the hottest and sort of what people are spending a lot of time on right now, certainly privacy-preserving machine learning. So being able to ask queries about particular machine learning models, maybe talking to ChatGPT and getting sort of a ZKP out of it. To give you some context, about 2 years ago, it would have been impossible to even generate a zero-knowledge proof of one layer within GPT-1 or GPT-2. But in 2023, you can actually generate a zero-knowledge proof for a single run of GPT-2 in under a few minutes. So we've had a huge increase here, but it's sort of still an abstract thing. Another thing that's very popular this year is incremental verifiable computation. This is sort of a kind of area of making these kind of proofs more efficient, such that you don't have to actually do the computationally intensive steps often. And then finally, of course, succinctness, right? The reason that ZK rollups have this benefit is they effectively represent the entire state transition of the state machine as a single fixed size object. So I can have many transactions represented by a constant size object. And this, allows for things like, say, for bridges, transaction batching, etc. But these are all pretty abstract benefits of a technology, right? Like, okay. If I go on the street, and maybe Singapore is a little better for this type of test, but like if I went on the street and was like, hey, here are 3 things that are amazing about this technology that there's like 11,000 people in this auditorium looking for, they would probably just be like, you're kind of crazy. I don't understand why I would care about these. And in a lot of ways, if we juxtapose sort of ZK and homomorphic encryption with the way people think about AI, you can find a lot of people who are, would say that, hey, look, I don't really get why I need to care about this. So, if we take a step back, maybe a better question to ask is, what are benefits that everyone can appreciate of these technologies that, maybe today don't exist, but in the next, 5 years, we actually will see people make moves on them. The first, and so, the last 2 talks from Sriram and Sergey talked about verifiability and being able to verify that computations are done correctly. But the second question, which is a little more than verifiability, is what's known as auditability. If something is not valid, if it's incorrect, can I figure out why it's incorrect, right? I can verify that A implies B, but I might not be, if I tell you that A doesn't imply B, I can't tell you where the mistake happened. The second thing, of course, and this is really what rollups are, is compression. And at some level, rollups are very special purpose compression algorithms for compressing a particular virtual machine in a certain way. But if you think about it, the reason you're able to watch YouTube right now is tons of improvements in compression over time. So what applications actually benefit from verifiable compression? Okay, so auditability. I think, again, people in crypto land always talk about verifiability, but one question, again, a question that's quite important is how can you go a step further? So on a podcast once I said this colloquially, and then people decided to make this meme out of it, so I think this is sort of the trilemma of auditability, which is the sort of 3 things you might want. Is it easy to tell if I got fucked? Is this thing efficient? And do I have any privacy? And there's some sense in which you can't get all 3. So what does it really mean? And again, this is just more to give some formalism to this, which is verifiability is any user can validate that a state transition that took place was correctly executed. I have an initial state, I have a final state, the transaction that took me from one to the other, anyone can validate. Auditability says if it is an invalid state transition, can I figure out where it's invalid or why it's invalid, which is a stronger property. So an example of this that's actually quite important, and this is actually the example that the US government is using in their case against Google, Department of Justice antitrust suit, which is the second price auction. And a verifiable auction is maybe 10 people submit bids. Think of an NFT auction, think of an MEV auction. And I can verify that, hey, look, the person who was supposed to win the item, say the second highest bidder, or the first highest bidder, actually received the item as expected. On the other hand, if, say, the auctioneer cheats and adds fake bids or manipulates the auction in some way, a question you might ask is, can I figure out which of those fake bids were actually from the cheating auctioneer, right? And the auctioneer might have done that to increase the price that people pay, right? And so a natural question is, like, how do you get to these mechanisms that can do that? So let's look at some applications that exist within crypto where auditability does matter and things actually have become quite important. So the first, of course, is MEV auctions. MEV means minor extractable value. It's sort of things where people can extract excess value from adding transactions, censoring transactions, or reordering transactions. And right now, these auctions, especially in post-Ethereum's merge, rely on sort of semi-trusted actors, the relayers and builders. And you can't really audit if they don't include your transaction correctly or they put someone else's in front of you. There's actually no auditability. And in fact, this was exploited in the April 2023 malicious proposer attack, where there was $11 million lost. One of the largest sort of like consensus bug errors ever. The second, and this is why I think about this, what my company does, is sort of on-chain risk management. So as risk management gets more complex, as you have many different layers of different pieces that have to combine together to keep a complex system safe, being able to attribute which components had errors and being able to figure out which components caused particular errors and not just know that there exists an error is extremely important. Understanding how those collapses happen is sort of the way that you get DeFi to be much closer to CeFi. And finally, there's a kind of boom in this notion of intents or preferences, which effectively corresponds to off-chain actors who are trying to satisfy some particular demand from a user. So Uniswap X, which just launched, is a great example of this. CowSwap is also another example of this. But you still, again, have these sort of off-chain actors whose transitions you have to actually know are valid. Okay. Moving away from auditability, if we go to compression, there's a lot of different ways that compression actually exists and is useful within ZK. And if you are kind of paying attention to sort of some of the investment worlds, I would say that a lot of the investment theses at the early stage venture side have actually implicitly been on applications that use compression. Zero knowledge machine learning, so like I said before, being able to have ChatGPT prove to me that it actually answered the query I gave it. This is not science fiction right now. Like, you can actually do this. It's not super fast, but it's actually, making a lot of progress. And in a lot of ways, that progress has come from compressing how you do that calculation. The second thing is, I think these need to get switched, but the second thing is sort of co-processing and light clients. So, right now, if you use a DeFi app, how many of you have used a DeFi app in the last 2 years? How many of you have used the front end versus use a front end provided by the team? How many of you have used Etherscan? That's a bad sign, right? The fact that like actually you have to go to this trusted third-party site to actually send these transactions is kind of an anti-pattern. In a world where you don't actually really need front ends and your wallet can actually answer all the queries necessary to interact with all these apps, you effectively need lots of light clients that are able to keep track of the state of all these apps and make it easy for your wallet to do certain interactions, and also make it so you don't have to send so many transactions. And the compression from ZK, especially in ZK Lite clients, allows you to really do a lot of these types of batching operations more efficiently. And finally, autonomous worlds. This is sort of on-chain games that are really on-chain. How do you make them have gameplay that looks like anything like Web 2 gameplay? And compression is extremely important to that. So for the ZKML side, I think there's been a lot of algorithmic improvements this year, and then people have been able to implement those improvements, and that's why we have had this 100+x speed up this year to make ZKPs of GPT-2. But there's sort of a lot of other stuff that's quite important to do. And what we're seeing is that the compression aspect is the most important part to generating proofs of verifiable machine learning, where you can really know that the model did what it's supposed to do. On the other hand, for light clients, everyone has probably implicitly used a light client, but you don't even maybe realize it. It might be hosted via your RPC provider. It might be hosted by the front end of the application you used. Soon you should be able to run that on your own. And there have been a ton of advances in things like data availability sampling, a bunch of things that Tarun mentioned, also stuff like Celestia, effectively reduces the overhead for running a light client for end users. And this makes modular design practical, and it also makes these applications like things like FriendTech a lot more easy to deal with. And co-processing is sort of another kind of extension of this, of being able to have a smart contract verify compute that's done off-chain via, say, a machine learning model. Finally, we have sort of the autonomous world thing, and this is taken from Scott Sonardo of Argus. And what happens is that blockchains inherently sort of have this slow game tick, right? Each block update is like the tick of a clock. But if you think about video games themselves, they don't necessarily have one main core loop. They oftentimes have many different speeds. Different characters, different agents are moving at different rates. So how do you homogenize all of that? How do you handle having multiple state updates for a single actor? And one way is to compress those state updates and only commit them infrequently. So the end user might have one user might have a very fast game clock, one might have a very slow game clock, but they can synchronize by just posting these kind of infrequent proofs. And we're starting to see people build game engines that take advantage of ZK for doing this precise type of compression. So with that, there's sort of three things that you want to take away from this if you don't remember anything else. ZK is more than just about privacy and rollups. Auditability, being able to figure out what went wrong, not just that something was wrong, is extremely important and something that's only uniquely enabled with these new technologies. And finally, compression is one of the main benefits that ZK has to making a lot of off-chain and on-chain interactions look the same and become more seamless. So with that, thanks.